Alright, this video is from Chapter 3, Section 3, and the topic is logarithmic functions and their graphs. What you'll learn about in this video are inverses of exponential functions, common logarithms of base 10, natural logarithms, base e, graphs of logarithmic functions, and an application of measuring sound using decibels. And why we learn about logarithmic functions: they're used in many applications, including the measurement of the relative intensity of sounds. One of the things that we look at is changing between logarithmic and exponential form. So in general, if x is greater than 0 and b is greater than 0 but not equal to 1, then we say that y equals log base b of x if and only if b to the y equals x. So this is how we convert from exponential form to logarithmic form and back to exponential form. So when we talk about a logarithmic function, we say that it's an inverse of an exponential function. So our blue curve here represents the curve of an exponential function. The red line is the line y equals x. Anytime a function is an inverse of another function, its graph is a reflection across this line y equals x. In the blue function and its inverse, the y and the x coordinates switch. So here we see that play out. We have our black curve is the graph of y equals log base b of x. So if I take a random point on the exponential function b to the x, and it has general coordinates x, y, then over here the inverse of that function and the inverse of that point, the coordinates will be yx. Okay, so just to associate some numbers here, let's just say that this point had coordinates 3, 8. Then that means that in the inverse, those coordinates would be 8, 3. Just to give you an example. So some basic properties of logarithms. Assuming that b is greater than 0 and not equal to 1, and x is greater than 0 and any real number y, then we say that the log base b of 1 equals 0 because b to the 0 equals 1. Again, just using our exponential notation to verify. Log base b of b equals 1 because b to the 1 equals b. Log base b of b to the y equals y because b to the y equals b to the y. And b to the power of log base b of x equals x because log base b of x equals log base b of x. So just to look at some values here associated with an exponential function and its inverse, here on the left we have function f, which is 2 to the x. And we have some x values in the domain of f. So when x is negative 3, the value of f is 1/8. When x is negative 2, the value of f is 1/4, and so on. When we look at its inverse, we see that relationship, what I was mentioning on the graph, play out. In the inverse of f, okay, this is f inverse of x, which would be log base 2 of x. 1/8, an x value of 1/8 produces a function value of negative 3. When x is 1/4, it produces a function value of negative 2, and so on. And you can see here in the exponential function, the inputs are the outputs of its inverse, and the outputs of f are the inputs of its inverse, and that's the relationship between a function and its inverse. So when we talk about logarithms, there are two bases that we use most of the time. And the first one is base 10. We call that the common logarithm. The common logarithm, log base 10 of x, we just write as log x. So anytime you see log x with no base here, we can assume that's a base 10. The common logarithm is the inverse of the exponential function y equals 10 to the x. Some basic properties of common logarithms. Let x and y be real numbers with x greater than 0. Log 1 equals 0 because 10 to the 0 equals 1. Log 10 equals 1 because 10 to the first equals 10. Log 10 to the y equals y because 10 to the y equals 10 to the y. and 10 to the power of log x equals x because log x equals log x. So these are just variations of the properties that we looked at a few moments ago of a general logarithm, just written in common logarithm form. We need to be able to solve some simple logarithmic equations. Solve the equation by changing it to exponential form, log x equals 4. So go ahead and take a second, solve that, and then when you're ready, play the video. So if we change log x equals 4 to exponential form, we come up with this equation right here. And then we can simplify that. 10 to the 4th is 10,000. So x would equal 10,000. So a fairly simple equation to solve. Again, it's just a matter of understanding how to take something in log form and write it in exponential form. So basic properties of natural logarithms. Now natural logarithms are, if we took log and we had a base of e, that's called the natural logarithm, but we don't write it that way. We distinguish natural logarithms from other logs by using ln. So ln of x. ln of x, or the natural log of x, is assuming a base of e, log base e. So if we let x and y be real numbers with x greater than 0, these properties are going to follow much as the same as the common logarithm and then just the general logarithm. So you can take a look at those properties, and again you'll find that those are identical to our logarithms that we looked at before, just a different base. So if we compare the graphs of the common and natural logarithm, you can see the blue curve here we have the common logarithm, and the red curve here we have the natural logarithm. And you can see that both graphs are asymptotic on the y-axis. Okay, and what that means is that x cannot equal 0. So these functions are not defined for x equals 0, and also they're not defined for x less than 0. Okay, so the domain of a log function or a natural logarithmic function, the domain is this, 0 to infinity. So describe transformations that will transform f of x equals the natural log of x to g of x equals 2 minus 3 times the natural log of x. So again, you know, in this course we are hitting transformations of functions. It's going to be something that's going to, you know, every function that we look at, we're going to look at, okay, transformations. How do we transform these functions? How do we go from the parent function to some other function that's based off the parent? And what we know is that, you know, here is the actual function part of this, natural log of x. So if we are multiplying the natural log of x by 3, we know that that's going to involve a vertical stretch. Now the 3 is negative, so that's also going to involve a x-axis reflection. And then we have this other 2 here. That 2 is being added to the function values, so that's going to involve a vertical translation. Okay, so again, if we see just the natural log of x, parent function, standard graph that we just looked at, but when we start adding coefficients and adding things to the function itself, then we get these different transformations. So here's a summary of that. So to solve this algebraically and to rewrite this algebraically to see in you know what's more intuitive to us, we could rewrite 2 minus 3 times natural log of x as negative 3 ln of x plus 2. This would be negative 3 f of x plus 2 if we wanted to write it back in terms of f. So g can be obtained by reflecting the graph of f across the x-axis, stretching vertically by a factor of 3, and then shifting upward 2 units. So here we have our natural log function. Okay. Here we have the reflection of that across the x-axis. And then this curve here is negative 3 times the natural log of x. So there's our vertical stretching. So you can see that stretching behavior. And then the last part of this would be to translate it up 2 units. So here is the final result, or the end result. So our stretched graph reflected across the x-axis has now been translated up 2 units, and that's what this looks like. Again, compared back to the natural log function, the parent function. So here's an application of logarithms. The level of sound intensity in decibels is beta, that's what this symbol is, Greek letter beta, equals 10 times log of I over I naught, where B beta is the number of decibels, capital I is the sound intensity, and I naught, which has a value of 10 to the negative 12th power, is the threshold of human hearing, which is the quietest audible sound intensity.